Hello, this is the Code Critics. In this episode, we are going to talk about naming in Python, how to choose good names, and what to consider when picking names. Most of the examples will focus on the names of variables, but the same guidelines apply to the names of constants, functions, classes, and packages. Let us start with the naming conventions provided in PEP 8, the Python style guide. As you can see, apart from constants, classes, and type definitions, Python expects names to be in lowercase. With the exception of packages, underscores in names are fine. Class names and type definitions should use camel case. Note that many Python libraries are wrappers around C or C++ libraries, and sometimes deviate from PEP 8 to be consistent with the naming style of the underlying library. In general, it is better to be consistent with an existing naming style than to follow PEP 8 if it breaks consistency. Keywords in Python, such as class or list, should not be used as variable names, but if a similar name is needed, the recommendation is to append an underscore to avoid conflicts. Python does not provide strong encapsulation, but the intent of a member variable is indicated by leading underscores. Protected member variables are marked by one leading underscore, while private variables are signaled by two underscores. Finally, there are special variables or function names, such as init, file, or package version, that are marked by double underscores at the beginning and the end of the name. The naming conventions in PEP 8 are largely limited to the syntax of names, and not very helpful when it comes to actually finding names with good semantics. Let us compare some examples of good and bad names. Generally, it is a good idea to pick the plural for data structures that contain many items and the corresponding singular name for individual items. For instance, when iterating over a collection of addresses, it is good to call the collection addresses and the individual address address. In contrast, non-matching names such as address and person list are better avoided, and especially data types such as list or dict should not be part of the name. If the scope of a variable is very small, such as in a list comprehension, it is perfectly fine to pick a single letter that matches the collection name. When looking at the example here, there is no confusion about what A is, and the variable name A is limited to the list comprehension. In general, the smaller the scope, the shorter the name can be. For index variables in loops, it is common practice to pick single letter names, such as I, J, and K. Longer names are generally not helpful and are actually confusing, especially when it comes to nested loops. It is often helpful to add a semantic prefix to clarify the role of a variable. For instance, n for number of rows instead of just rows. Dictionaries are commonly used to map data of one kind to data of another kind. For instance, a person's name to his/her address. The name of the dictionary should make that mapping clear. In this example, the meaning of address of Stefan or address of name is obvious, while person_data of name is not. In general, names such as data or items do not convey any useful information and are better avoided, even as parts of names. Sometimes it is necessary to further clarify the mapping by explicitly stating what is mapped to what. Here, RGB codes to color names. calling col or name for a tuple of numbers is not sufficiently clear. Here a few more tips on what to consider when choosing names. First, be accurate with the naming. For instance, a file is not a file name, and a file name is different from a file path or a file directory. These are common mistakes for names of parameters related to files. Be specific when picking names. Address is more specific than data, and RGB value is more specific than just color. Semantic prefixes can help to clarify the roles of variables. For instance, n_rows with just rows, or is_empty versus empty for Boolean functions. Use singular and plural matching names when iterating over the items of a collection. Don't encode data types in names. Data types may change, but we want names to be as stable as possible. Don't use existing Python keywords as names for variables or functions. Using list is a common mistake. Instead, use shortened versions or append an underscore to avoid such naming conflicts. The intent of functions or dictionaries that map data can be made clear by picking a name that describes that mapping. For instance, name to address. Finally, avoid confusion. For instance, the letters L and I and 0 and O are easily confused and are better avoided. Similarly, any names that are confusing due to misspelling or wrong meaning should be avoided. An important aspect we so far have ignored is the length of a name. How long should a function, variable or class name be? And the answer is it depends. It depends on three aspects: the scope of the name, its frequency, and the domain it is used in. If the scope is very small, for instance within a list comprehension, the variable name can be very short, just a single letter. There is no danger to forget its meaning or to confuse it with other names due to the limited scope. With increasing scope, the names generally become longer to avoid potential conflicts or confusion. Here, a longer variable name within a for loop, and even longer names for a nested for loop. Counter variables such as I, j, and k are a bit of an exception, but should be limited to loops with small bodies. The same is valid for class or function names that might even require namespaces to avoid naming conflicts across packages. In general, the larger the scope, the longer the name. Another factor that influences the length of a name is its frequency. Names that are used often can be short, since they will not be forgotten easily, and short names are faster to write and read. That is why we use abbreviations after all. Obvious examples are the names of frequently used packages such as numpy that are commonly shorted to np. Even one-letter names are perfectly fine, for instance for constants, provided they are frequent in use and cause no possible confusion. Alternatively, rarely used names or names that cover a wide scope should be longer, since they're easily forgotten and can result in name conflicts. Finally, the length of names is determined by the problem domain. X and Y are extremely generic and short and usually not good names, but they are the standard names in machine learning. Every user of the scikit-learn library will immediately know that X is the feature matrix and Y the label vector, for instance. Similarly, mathematics, statistics, and many other scientific domains, such as genomics, use certain standard identifiers that are better kept, despite being short or incomprehensible for the non-expert. To summarize, the length of a name is affected by its scope, frequency, and domain. Let's look at some examples. This first code example is from a blog discussing the effects of naming in data science. It is highlighted as an example of a bad naming, and indeed, the semantics, the meaning of this code is unclear. What are those features F1 and F2? Why are the data filtered for feature F1 greater or equal to 18? The code has, however, a positive aspect, and that is that its structure, the algorithm, is very clear. It is 2 short lines, and it's easy to understand what is happening here, but we don't know why. So the algorithm is obvious, but the semantic is obfuscated. The blog proposes this second version of the code as an improvement. And indeed, due to the better naming, the meaning of the code is now clear. It computes the mean height of adults. However, due to the long variable names, we now need a line break, a common issue with long names. And more importantly, while semantics is obvious, the algorithm is obfuscated. The long names hide the structure of the code, and there's also quite a bit of repetition. In general, there's a trade-off. Short names reveal structure, while long names reveal semantics. The trick is to hit the sweet spot, which depends on scope, frequency, and problem domain. Here an implementation that tries to hit that sweet spot. First, we use PD for Pandas, since that's an established standard. Second, we replace the rather abstract name physical data, which could describe trees, dogs, or chairs, by the much more specific name people, since that is what we are talking about here, the age and height of people. Third, we define a Boolean function isAdult to filter for adult people. Note the semantic prefix is, which is common for predicate functions. Finally, we write the entire processing pipeline in one line. Note that the right side is now a very readable description of the process. Filter people for adult, take their heights, and compute the mean. Since we have code that is easily understood on the right, we can pick a shorter name such as height adult on the left. Let's talk a bit more about data processing pipelines, since they are common in data science. When processing large amounts of data, pipelines need to be lazy and use iterators or generators to process data bit by bit, without loading the entire dataset into memory. Here a toy example of a lazy pipeline using Python's iterators library. As you can see, the code is rather difficult to understand. We can break this pipeline into bits and assign variable names to intermediate results. But finding names that truthfully and completely describe the content of those intermediate variables is either difficult or leads to very long names, as shown here. Furthermore, breaking the pipeline into pieces makes it harder to understand how the data flows through the system. A method to get around these issues is to define filter and processing methods that then can be combined to build the entire pipeline, as shown here. While the last line describes the complete pipeline, the nesting still makes it somewhat hard to read. Data flow languages such as Spark or NutsFlow avoid this nesting syntax and allow to write the pipeline as a sequence of steps. Here the same code using NutsFlow, where the individual steps and the flow of data is clearly visible. When we consider deep learning, we not only have data pre-processing pipelines, we also have tensors. Similar to data pipelines, code that uses tensors can be difficult to understand, since tensor dimensions are not named. Here, a toy example with a tensor describing a 3-channel image and computing of the sum over the channel dimension. Often, comments are needed to make such code readable. However, recently, since PyTorch version 1.7, so-called named tensors were introduced. Here an example that shows how to assign names to tensor dimensions. Functions can use names of dimensions, and result tensors maintain dimension names in many cases. Here we compute the sum over the channel axis C, and the output tensor has the correct dimension names height and width. Named tensors, however, are limited to PyTorch, and not all functions that process tensors can handle named dimensions as well as in this example. An exciting alternative is the einops library. Instead of naming the dimensions of tensors directly, the einops library instead provides functions that describe the transformations of tensors based on dimension names. Here an example that again computes the sum over the channel axis C of an image. Note that the dimensions of the output tensor are not named, but that the reduced transformation is using names, which makes the operation very readable. The einops library has the advantage that it simplifies many tensor operations, makes them much more readable, and works with various backends such as PyTorch, Keras, and TensorFlow. Let's summarize. First, be accurate when picking names. Files are not file names, and file names are not file paths. And especially don't lie. Names are used to construct a mental model of how things work. If you call a dog a chair and try to sit on it, you will be surprised. The same with names. Names should be brief. We want to solve problems and not write novels. The length of a name depends on its scope, frequency, and domain. But there's always a tension between long names that reveal semantics and short names that reveal structure. Don't encode data types in names such as in address list. Python functions generally work equally well with lists, tuples, or sets. And adding a data type such as list to a name implies a restriction that often is not true. Furthermore, if the type of a variable changes later, there is no need to fix its name. Consistency wins over PEP8 and personal preferences. If there's an existing code base with an existing convention of naming, use it. It is important to avoid confusion, and breaking conventions usually leads to confusion. When picking names, try to anticipate potential confusions and avoid them. All in all, code should read like a nice, simple recipe. This is the input, then this happens, this is what I get, and so on. And that's it. Thank you for listening.